Let's start with the exercise 3. Exercise 3 in Everest book, page 311. Determination of the order of fringe. The adjacent figure is a top view of Young's double slit experiment. O is the center of the central bright fringe. Given d equal 2 meters, the distance between the two slits small a equal 0.5 millimeter, lambda, which is the wavelength of the incident light, equals 500 nanometers, and we have a point M on the screen. M is located by the angle theta between the horizontal line and the line joining this point to M. This is the angle theta. Theta equals 4 times 10 to the minus 3 radian. Determine the order and the nature of the fringe whose center is point M. So we are going to determine the nature of the fringe at point M, whether bright fringe or dark fringe, or neither bright or dark. Okay, and if it is a bright fringe, we have to determine also its order, and if it is a dark fringe, we have also to determine its order k. But if it is neither bright nor dark, therefore we cannot obtain the order anymore. Let's start solving this exercise. If you remember from the course, for M to belong to a bright fringe, this implies that a condition must be satisfied. A condition must be satisfied. Which is the optical path difference at point M must be equals to k lambda. And k is the order of this bright fringe, if any. Therefore, let's check first whether M belongs to a bright fringe. So we have to check whether this condition is satisfied. This condition is satisfied means that k must be an integer, that is 0 or 1 or 2 or 3, etc., etc. First of all, let's return back to the geometry. This distance from O to M, we call it x, which is the abscissa along the x-axis, the abscissa of the point M. You can notice here we have a right triangle. This is my right triangle I'm speaking about. You can notice that tangent theta equals the opposite, which is x, over the adjacent, which is d. This implies that the abscissa x of point M equals d times tangent theta. But since capital D is much larger than small a, this implies that tangent theta approximately equal to theta, therefore x equals d times theta. So x equals d times theta, that is 2 times 4 times 10 to the minus 3 meters. So x equals 8 times 10 to the minus 3 meters. This is x. Why I have determined x first? Because from the course, you know that the optical path, the difference delta at point M equals ax divided by d, divided by d, divided by d. So by knowing x, knowing a and d, we can determine delta, and that's very simple. This implies that delta at point M equals a, which is 0.5 millimeters times 10 to the minus 3 meters, times x, which is 8 times 10 to the minus 3, divided by d, which is 2 meters. Therefore, delta at point M equals 2 times 10 to the minus 6 meters. This is delta. But if you remember, for point M to be a bright fringe or to belong to a bright fringe, delta at point M must equal to K times lambda. Let's check for this. For M to belong to a bright fringe, this implies that, as I have said before, delta at point M must be equal to K, certain constant, certain integer, times lambda. This implies that K is delta divided by lambda. That is 2 times 10 to the minus 6 divided by 500 times 10 to the minus 9. Okay? Therefore, it's 2 times 10 to the minus 6 divided by 5 times 10 to the minus 7. That is, it's 20 divided by 5, which is 4. This implies that K equals 4, which is a positive integer. This means that the condition of a bright fringe is satisfied, and hence M belongs to a bright fringe of order K equals 4. That is, M is on the positive side of O because it is along the x-axis.